Thank you for inviting me. I'm sorry that I could not make this in person. So I'm going to talk about person re-identification tracking in multiple non-OLED cameras. These are the two interrelated topics, and actually the person re-identification is special case of the tracking in non-overlapping cameras. So let's get started first with person re-identification. So person re-identification, the idea is that you are given a query image and you want to retrieve the images which are similar to query image from a gallery. And query and gallery images are captured by different cameras. And so this can be considered like a cross-camera data association problem. So given a query image like this, we want to retrieve say top 10 images from the gallery, and the green one are the correct one and the red one are the incorrect one. So the challenges are there's illumination condition can vary. As you see in this example, it's very difficult to see where the person is. The observable body parts may vary because it's covered by the umbrella, some of these head and so on. And posture can be different from the gallery to the query image, and background clutter, and also occlusion. So standard approach for solving this problem is what is called person classification network. So you're given an image like this, and you want to learn good features. Once you learn the features, then you can use those features to retrieve the corresponding images from gallery. So for each person, you will have several training images and they have ID, and you want to train this network so that you can learn good features. So we have two methods I'm going to discuss, one from CVPR 2018 and other last year from ICC 2019. So the first method, the idea is that we want to use the human segmentation, the part segmentation to help solve this re-identification problem. So also other thing we have done is we are using large number of data set and train the system so that we can get good features. And once you have features, then we can retrieve the corresponding images from the gallery. So we call this SPREID, which is human semantic parsing for person re-identification. And so this is our network. So this has the two parts. The upper part is the standard network that we start with an image, exception v3, we get these features, 2048 channels, and with the global average pooling, and we get these 2048 dimensional global feature vector for an image. Then we have a lower branch which deals with the human semantic parsing. So we take an image, again, compute some features, and after the soft mix, we get these 5 images corresponding to 5 semantic regions. And what we do then is take these different channels of the semantic segmentation and go and multiply with them these global features and select the global feature corresponding to these different parts of the body. And so now we have the foreground features, and then we have the body part features, which are the 4 other semantic parts, and we average them. So that way we have concatenation of global representation, which is from the upper branch, and then foreground representation, and then we have body part representation. So we have 3 2048 dimensional feature vector. And that's what we use to retrieve these images from the gallery. So we have used 3 data sets, the Hong Kong, Market, and Duke. So these are the typical results from Hong Kong. So query image shown on the left, and these will be the retrieve images when you will use the inception v3 with fine tuning of these data set. As you see, there are several incorrect images, and this is after our method. We get all of these top 10, which are correct one, another example. Again, couple of them wrong here, and we get all of them correct after applying one method. And more example. Here, somehow this is a difficult example. We still get a couple of them wrong, which is not what we expected. Another example, again, here we get most of them correct. Only the last ranked one is incorrect. So similar results for market. And this is also very difficult query image. And we somehow get confused with this motorbike. And this is another one. Here we get all correct. And one more example like that. So we have same thing for the Duke. We get pretty good results. Almost everywhere we have pretty good results. So now we can look at the quantitative results and use these MAP and rank 1 and rank 5. These are the state of art results the time we published paper. And then without semantic parsing, we still get pretty good improvement. But when we use the with semantic parsing and re-ranking and so on, we get a huge improvement, which is very, very nice. Same idea for the Hong Kong. Again, we get pretty good improvement. And then also for the Duke one, as you see here, from 60 to 84%. So in summary, we have very simple deep CNN network, which outperform the current state of art at that time we published paper. The main thing we did here that we used the several data set to train the network, and that provided large number of images. And also we use the semantic segmentation, different body parts of a human, and that helps. Okay, so now let's go to second piece, which was published last year in ICCV. And so here, again, revisiting, as I explained earlier, that simple approach for person classification approach is used for the re-ID problem. So we have an image and we know number of examples for each person, their ID, and we want to use the training images to learn these good features. Now, that is the most simplest one, that's person classification network. But there are some other approaches recently which have been used. So second approach is called verification network. So there, this is basically like a Siamese network. So there we want to, given two images, we want to come up with similarity and dissimilarity between two pair of images. And that's the way we learn the features. Another approach is applying the triplet loss. So instead of two images, we will have three images. And so the idea is that we have a query, we have positive example and negative example, and we want to learn the features so that positive example is close to query and negative is far away. And now we don't have to do only three images, we can do four images. That's the quadruplet loss-based network. So again, the idea here is that we want to bring the positive image close to query and push away these negative images. So now, if you look at the kind of most general case, which is called diffusion-based network, in that, not only two or three or four images, we will consider all the images. So we'll come up with a graph like this. We'll connect each image with all other images, and then diffuse this similarity between these images. One simple way to use is a random walk and come up with these probabilities going from one node to other node. And so This has been popular, and this gives better results compared to these other methods. Now, this is good because it's using the contextual information between gallery images and the query image, not only just 2 or 3 or 4, and which is better metric. And but the problem is that it's not applying probe image as a constraint. So we want to fix that, and therefore our approach is called constraint clustering based network. So we want to take a probe image and cluster the corresponding similar images in one cluster and push these other images away from that cluster. So this is a query image, and then we have these other images for the training. And so we build a graph again as we did before for diffusion based network. And so then cluster these query image with the similar images in one cluster and push these other one outside. So our pipeline is that we have these two networks, the upper and lower network. So we start with a probe image, and these are the gallery images and images like that, and compute, say, resonate features for all of these images, and get this feature cube, 248, 12 by 4, and then we do these the comparison between the probe and each of the gallery images, and do the global average pooling, batch normalization, and fully connected and so on. At the end, we come up with the similarity and dissimilarity score, as we have talked about the SAMI's kind of network. And here we have these two vectors, the T vector, dissimilarity, and R vector, which is similarity between query or probe and all other gallery images. So that's we call a verification network. Now we have a top network, which we call CDS network, constraint dominant set network. So again, we get these features for the probe and gallery images. And then we do the global average pooling, and we come up with these feature vectors for each of these, 2048 dimension, do the ReLU. And then we come up with affinity matrix that how similar the probe images with each of the gallery images. And we come up with this, and also the gallery image with itself. So given this affinity matrix, then we send it to constraint dominant set, and which will give us the membership score, which is the X star. And from there, we will get inverse membership scores, which is X star D, and which is like a similarity and dissimilarity we have here. So we then combine these from this network by multiplying, and then we will get these final scores, similarity and dissimilarity like that. Now, one thing we do that we combine them, so we want to control the contribution from the constraint dominant set branch, which is the upper branch, and the lower branch, which is the coming from the verification network. So that is controlled by beta, okay? So then we use these classes here, and we learn all these things using these two networks. So now we can talk a little bit about, how the constraint dominant set works, and that's our main contribution, and that's what makes difference. So now dominant set is an age-weighted generalization of maximum click. It's a complete connected graph. And so idea is that if you are given a graph S, V, and we want to come up with subset of that graph S, for which these weights are positive, and all the elements in S have positive score, and the other elements have negative score. So this is a constraint for internal homogeneity, and this is for external homogeneity. So let's take an example. So we have, say, 3 vertices, and these are their similarities. And this is a dominant set, okay? Now we add additional vertex 4, and these are the similarities of 4 with 1 and 2 and 3. And this, for the weight for this is positive, and so therefore these is a dominant set, all 4 vertices, because their similarity is similar. So now if we add another node, node 5, now these are the similarities from 5 to other nodes, and this is very different compared to this one. And so therefore this weight W will becomes negative, and this is not a dominant set, okay? So now the question is, how do we find dominant set? And there's interesting work in paper from here, Pavan and Palilo. So they formulated that we can find the dominant set by solving this quadratic optimization problem. So if X is a solution for this, where A is the affinity metric and X belongs to simplex, which is shown here, then the X will give us the actually dominant set. So that's a pretty interesting result. And that's what we are going to leverage. Now, constraint dominant set is very similar, except that we are going to modify, instead of having this affinity matrix, we will have this additional term. So this IQ is basically the diagonal matrix, and here these elements in diagonal matrix are 1 correspond to the elements which are not in the constraint set, okay, and 0 otherwise. And then we can take this and solve this as we did before, quadratic optimization, and that will give us the solution for constraint dominant set. So now there are many approaches to solve this. One simple one is called replica dynamics. So it's iterative method, very simple, about 2-3 lines of MATLAB code. So you start with some initial estimate, and you take that and get a new estimate using this iterative scheme, and that works pretty well. Now, once we get the dominant set, those 2 networks, the upper verification and the bottom one is verification and upper one is constraint dominant set network. We have actually a 3rd network, which we call auxiliary net. And the idea here is that we want to leverage multi-scale features to increase the performance. And this has been observed several other papers also using, and that helps. So for that, let's say we have an image here, we get these features, there are different layers, so we call them these scales. So we have these 2 parallel networks, and they don't share the weights, and we take the lower one and we apply the triplet loss, and the upper one, we take this one, and the lower one, also we apply the cross entropy loss. So we have these 2 losses, we add them up like this, and we train this network for that, and we get these features from auxiliary net. So during the testing, so we are given a probe image, and we are given the n gallery images. So we will compute, so total we will have n+1 images, and we'll compute these features from the constraint dominant set, and then we will also have features from the auxiliary network, auxiliary net I just described, and concurrent these features, and then give it to affinity matrix, and then we will apply the constraint dominant set as I explained, say replica dynamics. So during testing, what we are going to do, that say, let's say this is a probe image, and we get the constraint dominant set. So these all are in that constraint set. It seems they are similar. And then we will get the 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 closest example to that probe image and use both of them as a constraint. So we'll have second level of these constraint amino set, and that will do it. That will increase the number of these matches, which is a bigger set, and we found out that actually helped us a lot. Okay, so after that, then we'll get these scores. So experiments we have done again on these three data sets, as I mentioned earlier, the first paper, Hong Kong, market, and Duke data set. And we have also done here that we aggregate features from 8 different data sets to train our model, and that helps. And we use the standard matrix, MAP and rank K. So first we did the ablation study to show that all these things we have done are making a difference. So these are for 3 data sets, and we can see that if you use a baseline just single data set, then we get these results. And then if you use the multiple data set, we can get improvement, as you see in these different data sets. Now, when we apply the constraint amino set on single data set, we get a huge improvement for 9%. And then similarly, we get improvement on the multiple data set. And here, auxiliary net improves further. And then multiple data set, auxiliary net, all that goes from 70 to 85, which is very good. So now this is a comparison between the state of art last year and our results. So we get about 1%, little more than 1.5% improvement. And this is on the market data set. We also get improvement here. And this block here is comparison with other diffusion-based methods. And on the top of those also we get improvement, as you see. So same story for the Duke. And here also we get some improvement. So we wanted to study the impact of the beta. As I say, we kind of balance how much importance we are giving to the dominant constraint amino set, and also how much we are doing the verification network. So as you see, the beta, when you increase, which means we are increasing importance of dominance, say, we actually get improvement, so which is good in all the metrics. And here it also says that regardless of the number of images per person, we can get improvement. So here it tells you that how the dominant set is helping. So what we are showing here, the blue ones are the probe, and the green one are the positive, and then the red one are the negative. So now if you use the baseline method, when you get these scores, similarity scores, then we have to have some threshold. So suppose if you put this threshold, then we get some green one, but as you see, we also get some red one, and some green one here actually we miss them because of this threshold. So when we apply the deep constraint amino set, then if there's this threshold here, then we get all of them. Green one on the top, and we don't get bottom green one, and we don't get red one here, so which is good. So also we look at this similarity or affinity matrix we have, which we can look at as like a heat map, that if we are learning, the features we are learning are good, then affinity matrix will be good, and then constraint dominant set algorithm will work better to cluster and give us better features, and vice versa. So when we start the first epoch, this is the similarity heap map, and then this is the ideal one that we want, that this is a different person, matches of a person with different person, and the diagonal one is the same person. That should be the highest. Now, when you go through different epochs, so as you see, we improve from first to 10, we have better diagonal one. And then here also, we can even get more improvement, get closer to this. So, which is good. Also, the example here is that, well, verification network, the bottom network, say will give us the ranking like this, and the red one are incorrect, and this one is a query. Then we do the constraint dominant set, go through this affinity, the molecular dynamics, and so on, and then we get something like that. Now you want to combine these, and then we get a better results, which are shown here as compared to each individual one. So in summary, we have for the first time use the dominant set clustering method and integrate it into deep neural network and optimize in end-to-end fashion. So we have the one-to-one correspondence between re-identification and constraint clustering problem. Also, we get the state-of-the-art results. So future work, we can actually use these dominant sets as the clustering laws. So this was about the second method for the re-identification. So again, revisiting this problem, so we have query image and we want to retrieve the top 10 images from the gallery. And now limitation of this kind of approach are, number one, that we are kind of dealing with like pair of cameras. There's a query and there is, the gallery. And also this is the single image based CID. Okay, so we want to address those issues. So now we want to get into tracking in multiple non-overlapping cameras. So we have been working on this tracking for a long time, and if you look at different configuration of tracking, so simple way is the camera is fixed and we want to track in that. Then other will be the multiple cameras, but they have overlapping field of view. So there we want to solve the handover problem. And the third case is that the cameras are non-overlapping. Again, all these are fixed. So the next category is that camera is moving, and we want to track in a moving camera. And then two cameras are moving with overlapping field of view, and finally cameras are moving and they're non-overlapping field of view. So actually we have done work in all these different configuration. For example, this was paper a long time ago. We did, this was probably one of the first method on solving the tracking across cameras in the overlapping field of view. So here we use the field of view lines as Q to hand over the ID from one camera to the camera. So as you see, we have three cameras, the green, the blue one, green one, red camera. And so we find by self-calibration these edge of field of view lines. So this red line here is edge of field of view line of the camera, red camera. The green one is edge of field of view of the green camera. So the idea is that if in this camera a person crosses the red one, then he will be visible in red camera. So then we can assign him or her the same ID as ID here. Now, if the person crosses the green camera, he should be visible in the green camera, and we should do handover of ID like that. So if you play this thing, so first person detected, assign new ID, he crosses the red one, he's visible in red, and then crosses green, is visible in green. So there's a new person here, red one, he stays there, then there's another person, blue one, he's crossing the red one and the green one, so he's visible there. Then finally this other person will cross the red and green. So now all these people, we have different ID, and we have done this in a fashion that their field of view are overlapping. So other configuration we look at where these cameras are fixed but they are non-overlapping field of view. So here's example we have. So we have 3 cameras. One camera is indoor, other 2 cameras are outdoor, and say the persons are coming in indoor, assigning different ID, and for some time there won't be any observation. Then they will appear in this camera. For example, the challenge then is to assign them same ID. So this person will appear here, assign same ID, and maybe some people will appear in this camera. Again, you want to assign them same ID. So there's a big complex problem because of this different camera gain, different illumination condition, indoor, outdoor, and that was 20 years ago. We worked on this, and no deep learning or anything. This was the classical computer vision method. We also did this work where we have one camera fixed, other camera moving, and again the blue track here is the same person and blue track in the right camera, and red is same as here. As you see, these tracks are very different. So this is a pretty challenging area of solving this tracking problem. So now multiple camera tracking, if you look at typical approach, is that assume tracking individual camera is solved, then we solve the handover or re-identification or track corresponding across camera. That's what we did in these 3 examples I showed you. Now, re-identification in a way is some problem of tracking, because if you look at even the single camera tracking, we do solve the re-identification problem in every frame, because we see people in frame 1, then similar people will appear in frame 2. You need to identify that this is this person, this is that person, and that's essentially is the re-identification, or that's what we mean by tracking. So the tracking is used to deal with occlusion, misdetection, and all these things. And now re-identification multiple camera tracking is harder due to even more, because viewpoints is changing, camera gains are different, and there's time delays and so on. That's a problem. So our approach is that we want to, in this third piece, we want to simultaneously solve the single camera and multiple camera tracking problem, okay? And we want to solve in a single framework. So this is a work was published in IJCV last year. And here also we are using the dominant set clustering idea. So if you look at, say, let's say we have 3 cameras and with non-overlapping field of view, and this is their field of view. Now we can solve the tracking within camera, and these are like tracks, different person. And once this within camera is solved, then we look at the cross camera tracking. So we want to say that while the screen is the same person, which is visible in 3 cameras, and so somehow even this camera, this track was broken, and but leveraging this multiple camera tracking, we can also find out that actually these 2 tracks can be stitched. And similarly, this is another person who's brown, and this is another person, okay? So that's what we want to do now. So our pipeline is we have say n camera, we assume human detections have been given. Okay, so we have the first step where we take these detections and use very simple overlapping constraint to get short tracklets. Okay, and each short tracklet is 15 frames. Then from there, we have first layer, we'll take the short tracklets and which will apply the constraint amino set. We'll get a tracklets, and then from tracklets, we'll have another second layer. We will get the tracks. Again, this is done now separately in each camera. Then we'll have third layer, which will take the tracks from different cameras and then do the association, and we'll get the final results. Okay, so let's look at first layer. So we have human detection. We want to do data association. We get the tracks. Okay, so so this is the kind of example. So these are detection. As you see, these are red bounding boxes. Some of them are missing. Some are incorrect given this, but we take these and get these short tracklets, which is 15 frames long. And given that, then we go here and we get the tracklets. We do the association of the short tracklets. And then finally, we get the full tracks for the whole camera. And each person assigned a different ID, and that works pretty well. So now, a little more details. So these are the different segments. Each is 15 frames long, and we just do the overlapping constraint. Whatever is close to the previous frame, we just associate them and get these short tracklets. So now we take these short tracklets and then make a graph. We connect each of these short tracklets become a node. We connect this node to all other nodes in these segments, and then edges are defined based on appearance and the motion constraint. We assume the constant velocity. So then take that, then we find the constraint dominant set. So this may be the first constraint dominant set, which is a track of a person, one person, green one. And this can be another dominant set, which give you a track of second person, third person, and things like that. So that is the way we get now the tracklets. Nodes here are the short tracklets, and edges are depending on the appearance and the motion constraint. And we just apply this constraint dominant set to get the constraint set. We remove that, we get the next one, and next one, and so on. So now, if you look at the second layer, it's basically same thing. Another data association problem. Now the nodes are tracklets. Then we apply the constraint dominant set to strip the tracklets, and that way we get the tracks. So now the third layer is where we get tracks in different camera, and we want to solve the data association problem, the cross camera non-overlapping field of view problem. So for that, let's say we have 3 cameras, and here we have these tracks. These are the nodes. So the subscript here represent the camera ID. So these are tracks of the camera 1, and it's a track 1, track 2, and so on. And similarly, these are tracks of camera 2, and these are tracks for camera 3, which we have got using our constraint dominant set approach. So again, we build a graph as we have been doing, connect these nodes with edges and using the same constraint. Now we apply the constraint dominant set method again on this one, and we find the dominant set. So let's say constraint is camera 1. So we use this set as a constraint, and we find out what are the consistent dominant set. So maybe we'll find this one, which is the first one. Now, as you see that this brown is the same person, visible in camera 3, camera 2, and camera 1, but his track was broken in 2. But using this, the third layer, we are able to actually say that this is the same person, and we are leveraging this information in other cameras, and we can strip this track also. So like that, we will get this track, and then we will get maybe another dimension set like this. Again, this was broken here, but the same person, and we'll have like that. Then this will be a singleton, just one element in a set. Then we will use the camera 2 as a constraint, and like that we'll get some of these dominant sets, and then camera 3 as a constraint. So like that, we will get these dominant sets, and then we want to merge these and come with a consistent sets. And for which we have this constraint. One constraint is that at most a track should be member of one dominant set in one camera, because it cannot be possible in two cameras. Other is that maximum number of sets that contain a track I should be the number of cameras under consideration. That also makes sense, but otherwise it won't be impossible. So using that, then we kind of assimilate these tracks, and that's the way we solve this tracking in non-Olympic cameras. Okay, so let me show you the results. We did these experiments on Duke dataset, which is the very large dataset, 8 fixed cameras, more than 2 million frames, and about 0 to 50 people per frame, and about 2,700 identities. And so some of these qualitative results, as you see, so we are looking at the camera 5, 2, 7, and 4. So we look at, say, this person, his ID is 714, enters here and exiting here in camera 4. Then he enters in camera 7. Again, we have same ID, 714. And then he goes to camera 5. So it comes here. So in 3 cameras, we have same ID. So we have solved the re-identification problem and tracking. Basically, these are the tracks we have. So another example here, that is ID 238. So this guy comes here and go all the way there. And then he goes camera 2, again entering here and going like this. And then entering here, going like that. Again, all these 3 cameras, we have same ID. Okay. So we have some more examples. You know, this is 212, camera 6, enter here and going like this. And this one then goes to camera 1. And so it's going like this to that. And then in camera 2, so going like this to that. And then here camera 5. So, you know, the another example here, camera 6, camera 8, and camera 1 and 7. Again, we have this person 1162. This is a track. First time camera 8, then camera 2, then camera 3, and then we have these videos here. So we are going to look at this person ID 371. So as you see here, so this person is visible here, camera 6, and it's going to go exit, then he enters here, camera 5. And after that, then he will enter camera 2. So which is here, and all those we have consistent ID, and we have solved this handover problem, re-identification problem. So now metrics are, these are the standard metrics for tracking. The green one, higher the better, the red one lower the better. And these are for multiple camera metrics. And so these are listed here, but the main important metric is an easy case. So in that case, we do pretty good, about 70%, about 10%, more than 10% improvement. This is the hard case. Again, we do about 5% improvement. And this is the hard case again. I think it repeat here. So these are the results for the multiple cameras. So this is test easy. We do pretty good using these metrics. And this is a test hard. Also, we do pretty well. So now we can actually close the loop because we started with person ID. We ID the single image. Then we talk about tracking and multiple non-developing cameras. Now we can go back to re-identification, but now video-based re-identification, because previous methods were image-based re-identification. So kind of, this kind of relates and kind of close the loop. So video-based re-ID is now instead of image, we are given a video clip queue. And so we have a gallery of clips, which is shown here. And we want to solve that. Now, traditional methods will focus on building better feature representation objects, building better distance metric, and finally rank images from gallery based on their paired was distance from query. So it's, don't look at the video. So in our approach instead, we use same features what we learned before and same distance metric, but we want to leverage the constraint dominant set for each query. Okay, and so we want to perform ranking or shortlisted clips, not all the whole set. So advantages are we take into account relationship between query and elements in gallery, and also on elements within the gallery. So we are using these both of these relationship. So here's example. So we have an input image and we have a gallery. So again, we made a graph. So this is a graph. So query is one node, and these other, this is a query, and other video clips from the gallery are the nodes. Again, we made a graph, and we find dominant set. And dominant set happens with this, and then we can evaluate. So we did that, and we applied this on Morse data set because that's the video-based VID. There's 6 synchronized cameras, about 1261 identities, and have some distractors, and these tracklets are 25-30 frame long. So suppose if the probe is this, we can get these kind of results. And this one, the green one, are correct one. And this is much harder case as compared to image-based. Some example here, we got on correct one, and so on. So we look at the metrics, and we can do pretty good compared to these other methods using, again, the dominant set. So in summary, we talk about the single framework for multi-target tracking in multiple non-overlapping cameras. There were 3 layers of hierarchical approach, 2 layers within camera tracking, and the 3rd layer across camera tracking. And we also can solve the tracking and video re-ID multiple cameras. I show you example. And actually, we have a fast constraint dominant set algorithm, which I didn't have time to cover, which is much faster than other methods. And we got state-of-the-art results on the Duke data set and Morse data set for the 6 cameras. So this was about the IJCV paper. And so just to summarize the whole talk, so I talked about the person VID, where we use the human segmentation, different parts segmentation, and came up with a simple deep learning method, which performed instead of odd method that time paper was published. And we trained properly on large number of images, and that made a big difference. And of course, the semantic parsing helps us a lot. Then I talk about the consent dominant set for personal ID. So the previous approach, this one was simple verification network that we learn the features just based on we have ID. But in this one, we apply the diffusion based clustering that we want to use the query and other gallery images to learn better features, all of them, not just 2 or 3 like triplet loss or Siamese network. And then we did the clustering end to end, involving in the learn feature so that they do better clustering and so on. And so we have one-to-one correspondence between person ID and constraint clustering problem, and we got state-of-the-art results. Then we continue the consent dominant set approach for tracking and multiple non-overlapping cameras. And we have single framework for tracking within and across cameras. And we have 3 layers of hierarchical approach, and which solve tracking and video reality in multiple cameras. Okay, thank you.